Hey students, Mr. Danahauer here today. Today we're going to be talking about the different types of bonds that hold compounds together. The reason we're doing this at this point is we've talked about atomic structure, we've talked about all the different elements on the periodic table, but you know, there's only 118 elements on the periodic table, but we have thousands and thousands of different compounds that make up all the different things on Earth. So why is that? How can we have so many different things? And the answer to that is bonding. Bonding holds atoms together. There's different types of bonds, and so in today's lesson we're going to learn about the different types of bonds and how can we predict the type of bond that two elements are going to form. That's the goal for today. Now there's a couple of key things that we need to know, and I'd recommend that you be taking notes on this either on your own paper or the note guide that's provided for you on Google Classroom. First of all, we need to know what the term electronegativity means. The key thing that determines how elements are going to bond is their electronegativity. It's basically how hard atoms pull on electrons, and usually we're talking about their bonding electrons, which is also going to be the electrons in their valence shell or their outer shell. So the elements that have higher electronegativities are going to pull harder on bonding electrons or valence electrons. The atoms with lower electronegativities are not going to pull on those valence electrons very hard. We also need to know the term metal versus non-metal. But real quick, let's go ahead to the next slide really quick. Let me show you electronegativity values. So when we're looking at electronegativity values, those are typically values from 0 up to, we can see the highest electronegativity value of fluorine here, which is 4. And so down here are our lowest electronegativity values, and as we move our way up this way, as I'm moving, they're getting higher and higher and higher. So the elements down here, these metals in this corner, they don't pull on electrons very hard. As we get farther and farther, we're pulling a little bit harder, a little bit harder. Now we're starting to pull very hard on those valence electrons. Okay, so you need to be able to find on this periodic table that's provided for you on Google Classroom, you need to be able to find this number for this lesson. We're going to be using that quite a bit as we move forward. Okay. All right, now let's go ahead and go back. So the other thing you need to be able to do is determine from the periodic table if an element is a metal or a non-metal. We're going to be using that a lot as we determine the type of bond that exists. So if we go to another example, which if you were in class, you colored the periodic table with me and we created this dark stair-step line right here that's in black. So to the left, or in red on this periodic table, are all of the metals that exist. To the right are all of the non-metals that exist. But keep in mind that hydrogen is over here. It's over here because it only has one valence electron, and there's other reasons as well, but it is a non-metal. So you can see most of the elements on the periodic table, the majority of them are metals, whereas a very small handful of elements are actually non-metals. And actually the non-metals here, and not including the noble gases, the rest of the ones like carbon, nitrogen, oxygen, phosphorus, sulfur, those are the ones that are responsible for most of the elements that make up living organisms. And you guys know that there are so many different types of chemical compounds, different molecules that make up living organisms. Okay, so we're going to use those electronegativity values, and we're going to use the differentiating between a metal and a non-metal. For this, the metalloids, the yellow ones in here, we're not going to worry too much about those. Those are elements that kind of have both properties of metals and non-metals. Just remember, if it's on one side of the line or the other, that's what we use to determine if it's a metal or a non-metal. So let's practice. Use your periodic table, pause for just a second, and see if you can use, for each element, determine if it's a metal or a non-metal, and also find its electronegativity value. So pause and see if you can do that for about 60 seconds. Go. Okay, this is what you should have gotten. All right, for those answers. Again, if you're unable to do that, you need to stop and do some more research or ask your teacher questions, because this is critical to be able to do this before we move on to the next step. Okay, so again, we already talked about that the lower electronegativity values are in the bottom left corner, and the highest electronegativities are on the non-metal side around fluorine. And so in general, metals have a low electronegativity compared to nonmetals. Let's just say that in common terms again. That means metals don't pull on their valence electrons very hard. Nonmetals pull on valence electrons a lot harder. And as we talk about bonding, that's going to help us to understand why different kinds of bonds form. Okay, now let's talk about bonding. This is always formed by when electrons change. They either move from one atom to another, or they get shared between atoms. So why do atoms want to bond? What's their purpose? And the reason why is all elements, or most elements, want to have a full valence shell. And again, for most elements, that's 8 valence electrons. We've learned how to count valence electrons on our periodic table, and so there's only one group of elements that has a full outer shell. That's the group or column that's all the way to the right, and those are called our noble gases. And they don't bond with other things typically because they have a full outer shell. Now, the reason why the other elements bond is because they want to have a full outer shell. So an element that doesn't have a full outer shell can either get rid of some electrons, or it can gain some electrons, take some from another element, or it can share electrons with another element. And again, that's what brings up our different types of bonding here. Okay, I think I didn't mention the name of that is called the octet rule, and that's why I have the little octopus floating here. Octa stands for 8, and most elements want to have 8 valence electrons. If an element has 8 valence electrons, it has a full octet. So that's how we would use that vocabulary. Okay, let's talk about our two main types of bonds, ionic and covalent. And then if we determine something is covalent, we then want to determine, classify it as either being nonpolar covalent or polar covalent. Here's a little chart to compare the types of bonds. For ionic bonds, these are called ionic bonds because electrons move from one atom to another. And remember, when that happens, an ion forms, and we'll see that in some pictures in just a second. Ionic bonds form anytime we have metals and nonmetals coming together. So remember, metals have a low electronegativity, right? Nonmetals have a high electronegativity. So you get an element that doesn't pull very hard on its valence electrons, and another element that pulls really hard on valence electrons. That nonmetal is going to take electrons from the metal. That's the transfer of electrons from the metal to the nonmetal. That holds them together with the electrostatic charges. The metal is giving away negative electrons, so it's going to become a positively charged cation. The nonmetal is taking electrons, it's getting negative charges, so it's going to become a negatively charged anion. And it's the difference in charge that's going to hold those two elements together. Covalent bonds contain only nonmetals. So if you have two nonmetals that come together, they're both going to pull hard on valence electrons. That means that neither one of them is willing to give them up. That means they're going to be sharing those electrons. So the way that covalent bond forms is the electrons from one atom are attracted to the nucleus of both of the atoms, and they end up sharing those electrons. So covalent involves sharing of valence electrons, like co means together, and valent is the valence shell. Covalent is sharing. Ionic forms ions, and that's what holds those atoms together. Let's dig into those a little bit more individually. So in the ionic bond, I already said that transfer of electrons occurs from a metal to a nonmetal, and the ions are attracted to each other. So let's look at an example here. Here I have a neutral sodium atom. Sodium has 11 electrons, and it only has 1 electron in its valence shell. This is its outer shell, the one on the outside, right, the ring here. And then I look at chlorine here, and chlorine has 7 valence electrons in its outer shell. How many do they want? Well, both elements are most stable if they have 8 valence electrons. Remember, chlorine's going to want to pull really hard on electrons. It has a high electronegativity of, what's chlorine? I don't have it right in front of me. And sodium has a lower electronegativity, so it's not going to pull very hard on this 1 valence electron. So here's what happens. Sodium ends up giving its electron to the chlorine atom. Now look what happens. This valence shell is no longer full. It no longer has electrons in it. So now this inside shell is the valence shell. And look, it's full. And also we notice that it gives sodium because it gave that one electron away. It now has a +1 charge. And chlorine took that valence electron, here it is, the one that came from sodium, and now if we count up the outer shell in chlorine, it has 8 valence electrons as well. Both of these atoms, now called ions because they have a charge, see the charge for chlorine is -1 here, both of these have a full octet, and they are most stable that way. That's why we don't really see sodium, the metal, out in nature. It's very reactive, and chlorine is the same way, but we see sodium chloride, salt, all the time. It's a very common compound because when it forms it stays that way and it's pretty stable. Okay, so again, negative charges attract here, so we get a positive charge, opposite charges attract. Positively charged and negatively charged ions are going to want to stick together. That's called an ionic bond. Okay. Here's that as a visual for you. Okay, same thing, just a different way to show the electrons in this picture. Now let's talk about covalent bonds. Covalent bonds form when atoms share electrons, and this is always going to be between 2 or 3 or 4, 10 or 500, whatever, nonmetals. Anytime we get a bunch of nonmetals coming together, they're going to be sharing electrons. And remember, if the electrons are shared, we then have to decide how they're shared, and that's going to determine if we have a polar or nonpolar covalent bond. So here's a nonpolar covalent bond, and let's just focus on covalent for now. We'll talk about polar and nonpolar in a second. These two chlorine atoms have 7 valence electrons each, but when they come together, they end up sharing that pair of electrons, and now both elements have a full valence shell. They have a full octet of 8 valence electrons when they stay together shared, and they're going to be most stable that way because they have a full outer shell. Here's some other examples. We get a hydrogen atom here. It wants to have 2. Keep in mind, the octet is for all elements, but hydrogen and helium, they only can fit 2 in their first shell. And so sometimes people call that a duet for hydrogen, but if you say the octet for hydrogen, people know that you're just talking about a full outer shell. It's kind of a general term. So chlorine has 7, hydrogen has 1, hydrogen wants 2, chlorine wants 8. So when they come together, now hydrogen has 2 and chlorine has 8, and so they both have a full outer shell because of that sharing. Here's water. Again, I have 2 hydrogens and I have oxygen. How many valence electrons does oxygen have? It has 6, so it wants 2 more, and that's why it bonds with 2 hydrogens, because you get a pair here that are being shared. Those are both now oxygens and hydrogens, and we get a pair here that's being shared. So if we count up the valence shell for oxygen, it now has 8 valence electrons, and it's very stable as water. Same thing down here for what we call carbon dioxide or CO2. We get carbon, which only has 4 valence electrons. It wants 4 more. Each oxygen has 6. It wants 2 more. And so what happens is they end up coming and sharing 2 pairs of electrons on each of them. And that's called a double covalent bond. Each bond is a pair, and so this is a single covalent bond. This would be considered a double covalent bond. So we can get different bond types, but they are all sharing electrons, and the reason they're doing that is to get a full outer shell. Now let's talk about polar and nonpolar. This part is usually the more confusing part for students, so pay close attention, and if you don't understand it, make sure you ask questions. When we get 2 nonmetals that come together and they share electrons, they're each going to be pulling a certain amount on those shared electrons. So we can see these 2 chlorines right here. That pair of electrons is being pulled both directions, one by each chlorine. Now in this case, each chlorine is pulling the same because they have the same electronegativity value. That means there's no difference in pull. Think about this as a tug-of-war between the 2 chlorine atoms to get those electrons. It's like 2 guys who are pulling, and they have the exact same strength of pull. Neither one of them is going to go anywhere. Those electrons are going to stay right in the middle. That would be like if you're the tug-of-war, they're pulling this rope and there's a flag, right in the middle to see where the flag goes as the people are pulling on the rope. Those electrons would be the flag. they're not going to go anywhere if the two sides are pulling equally. And we call that a nonpolar covalent bond. When the electrons are shared equally, or there is no difference in electronegativity, meaning the atoms have the same electronegativity values, then that's going to be a nonpolar covalent bond. Opposite of that is called a polar covalent bond. So what if one atom is pulling those electrons harder than the other? If we look at this here, okay, chlorine is pulling a little bit harder than the hydrogen. I believe chlorine is a 3.0 for its electronegativity, and hydrogen is a 2.1. I might be off on that, but definitely chlorine is pulling harder than hydrogen. What that means is the electrons are going to get pulled a little bit towards the chlorine side. Now they're still going to keep sharing them, it's still covalent, but these negative electrons just get pushed a little bit and spend a little bit more time over on the side of chlorine. Now remember, what does that do? What effect does that have of the unequal sharing of electrons? Well, wherever the electrons are getting pulled towards ends up getting a little bit of a negative charge. And so we see that here. This is called the Greek letter delta. It's the same delta triangle that you use in math for the symbol change in. But this is the other, I can't remember, I think this is the lowercase delta right here, and the triangle is the uppercase delta. But I call it a fat bottom S. It looks like a S with the bottom kind of attached to itself. And it's a negative charge. This is saying that there's a partial negative charge on that side of this molecule or the bond. Why is that there again? Because these negative electrons are getting pulled towards the nonmetal with that little bit higher electronegativity value. Now that gives this side of the molecule a partially positive charge because the electrons are getting pulled away from the element that has the lower electronegativity value. They're still sharing, so they're not full charges like in an ionic bond. They're partial charges because there's just shifted a little bit to one side or the other. Okay, so it would be wrong to write a full negative charge here or a full positive charge here because they're not full charges. They're just slightly charged. Now, why is it called polar? Let's think about that. Poles on Earth. That's probably the most relevant connection for us, right? We think about the North and the South Pole. What would we call those? We would call them opposites. Something that's polar is going to have opposite sides. So here we see negative and partially positive, partially negative, partially positive. Those are the poles on that molecule. There's a partially negative side and a partially positive side. That makes that molecule act a little bit like a magnet. It has a little bit of a one side and the other, and when we put a bunch of those polar covalently bonded molecules together, they actually want to stick together a little bit like water because of those different charges that they have, the different partial charges. Now, again, just make sure we have, this is really key stuff to make sure you understand down here. In a polar covalent bond, the bonding electrons are shared unequally. That results in partial charges. And that happens whenever there's some difference in electronegativity. They don't have the same electronegativity. Okay. All right, now one thing that we want to do when we label polar covalent bonds is draw the dipole and the partial charges. This arrow with the plus on it, that's called the dipole or the bond dipole. The bond dipole is going to point in the direction that the electrons are being pulled more. They're going to point in the direction of the higher electronegativity. Like I said, I think chlorine is either 3 or 3.5. Hydrogen is like 2.1. And so chlorine is pulling harder on the electrons, so the arrow is pointing towards the chlorine here. Okay, so I just want to check, yeah, 3.0 for chlorine and 2.1 for hydrogen. So there's a big difference in the pole there. So that dipole is showing the direction the electrons are going toward. And then, of course, there's those partial charges. If the electrons are getting pulled this direction, that means since electrons are negative, we're going to have a partially negative charge here and a partially positive charge over here. Okay, good. All right. We need to practice a little bit, So what you should do now is stop and determine if for each one of these element pairs, if it would form an ionic or covalent bond. We're not going to worry about polar or non-polar right now. We just want to use, is it a metal and a nonmetal? Then it's going to be an ionic bond. Or if it's two nonmetals, then it's going to form a covalent bond. That's all we're doing for this one. So pause and just use that to determine the type of elements you have and what kind of bonds those elements are going to form. Okay, so what you should have determined is because calcium and sulfur is a metal for calcium and nonmetals for sulfur, they're going to form an ionic bond. Likewise with lithium and fluorine, because you have a metal and a nonmetal. But the next two, we have two nonmetals, chlorine and oxygen are nonmetals. They're going to form a covalent bond. And nitrogen, two atoms, nitrogen atoms, are going to come together and form a covalent bond because they're both nonmetals. When you're trying to decide what kind of bond is going to form, start by determining if it's ionic or covalent, by determining if you have a metal and a nonmetal, or if you have two nonmetals. That's always going to be your first step. Okay, now the next step is going to be determining if it's a if it's a covalent bond, is it going to be polar or nonpolar? And that's where we want to see, is there a difference in electronegativity? If there's no difference, if they pull equally, it's nonpolar. If there is a difference in electronegativity, one's pulling harder than the other, then it's going to be a polar molecule or polar bond. So if we practice each of these, first, this is the kind of culmination of what we want to be able to do. Determine if each is a metal or a nonmetal, then identify the type of bond that will form, right? We just did that in the last slide. Then if it's ionic, we want to determine if the element is going to be, which one's going to be the cation and which one's going to be the anion. Cation is positive charge, anion is negative charge. If it's covalent, we want to determine if it's polar or nonpolar, and if it's polar, we want to decide if there's, or we want to add the dipole and the partial charges. Okay, so here's the answers, guys. If we look at the first bond between magnesium and chlorine, we're going to see here that this is a metal and a nonmetal. And so when they come together, there's going to be a transfer of electrons, and we're going to get ions that form. Magnesium is going to give its electrons away to chlorine atoms, and it's going to have a positive charge, so it's going to be the cation. Chlorine is going to take electrons, it's the nonmetal, it's going to be the anion. Remember, metals in an ionic bond, your metal's always going to give away electrons, and metals will always become positively charged. Your nonmetals are always going to take electrons, and they're always going to become negatively charged. Okay, so ionic bond, and we've identified the cation and the anion. You don't need to go as far as determining the charge on each one. You just need to tell me if it's positive or negative for now. We'll get into charges later when we talk more about ionic bonding. The next one, a sulfur-carbon bond. So we look at this and we see sulfur is a nonmetal. Carbon is also a nonmetal, okay? And if we look at their we know this is covalent. Now we want to look at their electronegativities to determine if it's polar or nonpolar. 2.5 for sulfur, 2.5 for carbon. Remember, I'm just pulling these right off of that periodic table. For each element at the bottom, there's a place that shows you the electronegativity value, and it's going to be something between somewhere around 0.5 and 4, okay? So if you're finding numbers like 88.2, you're probably looking at the atomic mass. Don't use those numbers, that'll throw you off. Here we go, 2.5, 2.5. Do they pull equally or unequally? They pull equally. That means that the electrons are shared equally, and we will not form a polar bond. This will be a non-polar covalent bond because there's no difference in electronegativity between the elements, and the electrons are going to be shared equally. Okay. So non-polar covalent. Now let's come down here to the oxygen-fluorine bond. Oxygen and fluorine are both nonmetals. This is going to be a covalent bond. So the next thing we need to do is decide, is it polar or nonpolar? Let's look at the electronegativity values. 3.5 for oxygen, 4.0 for fluorine. So who's pulling harder? There is a difference in electronegativity. We know fluorine is pulling a little harder than oxygen. So this is going to be a polar covalent bond because there is a difference in electronegativity. Now let's look at the dipole. So the dipole arrow goes towards the element with the higher electronegativity of 4.0. That's showing the direction the pair of electrons here in this bond are getting pulled towards that fluorine. Okay, and we draw a little plus on the opposite side of the arrow. That gives our dipoles, it gives our partial charges negative on the fluorine side of the bond and positive on the oxygen side of the bond. Notice up here, they are full charges. There's no delta. Down here, they're partial charges on this polar covalent bond. So right now, what you should be able to do is define electronegativity, determine if an element is a metal or a nonmetal. Then you should be able to, given a pair of elements, determine if it's an ionic or covalent bond. If it's covalent, determine if it's polar or nonpolar covalent. And if it's polar covalent, be able to draw the dipole arrows, the dipole arrow and the partial charges based on the difference in electronegativity. If it's ionic, you should be able to determine the cation and the anion. That's all. Have a great day.